Good afternoon or morning, year 12. We are going to have a look today at starting some of the year 13 content. First though, I would like you to have a go at reviewing some of the stuff that we did about radical substitution. So here is an exam question for you about that. We have a 1 marker for part A, a 5 marker for part B, and then C is actually a 2 marker which got missed out. I'm going to pause here for a minute for you to have a go at doing that, and we'll have a little chat. Okay, hopefully you have managed to do that question. Our answers are, for the first point, we needed to have hydrogen gas and a nickel catalyst. Now, for part 2, it is important that you know initiation, propagation and termination. On this mark scheme, because it hasn't shown up on here, they have now become really picky about making sure that you're showing the radical dots. So don't forget that our chlorines here are radicals, that our chlorine here is a radical, and that we've formed this organic radical here. This one is our radical, and that means that we have reformed our radical over here. Don't forget as well that termination always involves 2 radicals, so like our chlorine radical here, our bromo-propyl radical there, our chlorine, and then our organic radical there. And we need to have linked initiation, propagation and termination. So you can see that in many respects actually there's not a lot that you need to write to get 5 marks, which is a lot of marks in this. Okay. For part C, don't forget that, well, we don't know exactly, actually no, we know that that is the molecule that we started with. Don't forget that for this point, which was a distinct one, that substitution at different positions along the chain, one of our problems is that it could have added here, it could have added up here, or it could have added over here. Yeah, we don't get to control where that chlorine atom is added on, is substituted in, and of course our further substitution would be if more than one of these substitution steps had happened. Remember, the ways to reduce that further substitution are to reduce the molar quantities of the chlorine that you're adding. So if you had a slight excess of whatever it is you're substituting, then you're going to reduce the chance of further substitution. It's not going to completely stop it, but it does help. So, today we're going to have a little look at monitoring reactions, and a lot of the monitoring of reactions isn't going to be something new. Okay, so don't forget at GCSE we had that rate was the quantity reacted or produced divided by the unit of time, typically seconds, should be seconds. We, though, want to make sure that everything is nice and consistent. So we have instead that the rate is the change in concentration of something divided by the time it takes to do so. And don't forget that for square brackets, that's our easy way of showing concentration of something. Yeah, that we talked about that when we were looking at KC earlier. Okay, so we'll use square brackets here a lot. Make sure that you get in practice of them. It really helps if you're laying out your working in a sensible way. Okay, and using nice little shorthands like that will help. Okay, so continuous monitoring. This is probably the way that we think of most of the time, and that's where you pick some quantity that you're going to measure. Now, depending on your reaction, that will differ. So if we had a gas, we'd measure maybe the volume of gas, or we could measure the change in mass of it. If we had a colour change, we could detect the intensity of that colour change. If we had a change in pH, we could detect a change in pH. And we would do that multiple times throughout the course of our experiment. So I've got a diagram below, magnesium plus some dilute acid. We've done this sort of experiment loads of times where we would measure the volume of gas produced, I don't know, every 5 seconds, 10 seconds, something like that. Okay, that gives us a set of results. and we would have ended up with a graph that looked like that if we were measuring the mass, or we would have possibly ended up with a graph that looked like that if we were measuring the total volume of gas that had been produced. We want our graphs to end up being consistent, which is why we're going to look at converting these sorts of results into concentrations. Okay? Now, I said you can use a colorimeter. If you do biology, I believe that you've used a colorimeter. The principle of it is nice and straightforward. We have a little sample vial here, which is called a cuvette. They're normally 1 centimetre square, so it doesn't matter which way around you put them in. And that's going to be filled with our sample of whatever it is. And what we do is we shine some light at it, and we have a sensor on the other side that detects how much light has come through. Now, when we do this, we will always set it up where we use the solvent that we're going to be doing our experiment in, so that we're not detecting the solvent in this absorbance. We get a reading which is called the absorbance value, and that will range from 0, where all of the light makes it through, through to either a 1 or 100%, and that's where all of the light is being absorbed. You might notice that I used green and red for my diagram. That's because we need to be careful about the frequency of light that we're using, because if I used green light to shine through, if I'm shining through something green, then all of that light is just going to pass through anyway, and it doesn't matter how green it is, I'm not going to notice any difference in absorbance. Now, this is useful because we can follow the concentration of some coloured reactant or product in our experiment. Just it on its own is not necessarily the most useful thing, although typically the absorbance is proportional to the quantity that there is. But what we want to do is we want to make a calibration curve. Okay, that's this doodad down here, or this is an example of one. To make that, all you actually do is you make up a series of different concentrations of the particular substance that you're measuring the absorbance of, and you chuck them into the colorimeter and you record the absorbance. You plot them on this graph, and that then means that when you're doing the experiment, if you got an absorbance of 0.6, you'd follow along and go down, and in this case you'd see that it was, 70%. We could also give that in moles per decimetre cubed, so that could be whatever concentration it is in moles per decimetre cubed. That would be how we would normally want to use it. Okay? Now, it's all well and good saying that we want to use concentration time. We want to turn those into graphs, and that sometimes is easier said than done. Okay, so if we had this example here, a student is using a balance to monitor the loss of mass over the course of the following reaction of zinc sulfate with 250 centimetres cubed of 1.5 molar HCl. We need to turn these masses into concentrations of hydrochloric acid. So as our mass is decreasing, that's because we're losing the hydrogen sulfide gas. Okay, so for each of these, the first thing that we're going to want to do is work out how much hydrogen sulfide gas that has been produced. So we do that by doing the mass at the start, take away the mass at a particular time. So if we did the first one as example, 411.02, take away 411.02, we amazingly get no grams of hydrogen sulfide have been produced, which should come as no surprise seeing as that's the start of the reaction. If we did the last one on the other hand, we have 411.02, take away 407.51, and that should give us a result of 3.51 grams. Okay, and we'd need to do that for each of those. Okay, once we have worked out the number of grams of hydrogen sulfide, we need to work out the number of moles of hydrogen sulfide that is. So if we take our, let's say our 3.51, we're going to do N equals M over MR, and our mass was 3.51, and we're dividing that by the MR of hydrogen sulfide, which would be 34, so we're going to get approximately 0.10 with some extra decimals. Okay. That then means that we have the capacity to work out the number of moles of hydrogen chloride present in our solution. To do that, we first need to work out the number of moles of hydrogen chloride that we had at the start of the reaction. Okay, so this is where, if I do this in a different colour, these bits of information are important. So the number of moles of HCl that we had at the start are 1.5 times 250 divided by 1,000, which is 0.375. Okay, so now that we have how much we started with, we can work out the number of moles that we have at a particular time by taking that number of moles and taking away from it 2 times the number of moles of hydrogen sulfide, and it's 2 times that because it's a 2-to-1 ratio. So, for example, at the start, we would have 0.375 take away 0, so we'd have 0.375. Yeah? Obviously, as the reaction progresses, we're going to get less and less and less. Okay, let's get rid of that, just because I've run out of space. Let's get rid of all of these bits. Okay. That's leaving us with our last little bit, which is turning it back into concentrations. So I always remember concentration as the number of moles times 1,000 divided by the volume. So, for example, for the first one, we have 0.375 times 1,000 divided by 250, and mercifully, that gets us 1.5 moles per decimetre cubed back. Okay? You would need to do all of those things for each of these times, and that will now give you the concentration of hydrochloric acid at each particular time. Then I would want you to plot it as a graph. Now if we plotted this as a graph, hold on, let's get rid of this writing. Now if we have done that, we would get these masses of hydrogen sulfide at these particular points, these numbers of moles of hydrogen sulfide at those particular times. I probably want to use more decimal places. That was my mistake in copying this across from Excel. Then we would do our number of moles of hydrochloric acid, take away 2 times the number of moles of hydrogen sulfide, and then we would convert those back into concentration of hydrochloric acid. So you'll notice that I've used nice shorthand at the top of these. Okay, that, if we plotted those, would give us a graph that looks like this, where on the left hand side, our y-axis is the concentration of HCl, and down on the bottom we have time in seconds. Okay. If we were wanting to work out the rate of this reaction, we would work out the gradient of it. Here you can see that this looks like it's a nice straight line, so if we did the gradient of that straight line, then that would tell us the rate of this reaction. Okay, I would like you to have a go now. Okay, so we've got a student is following the reaction between 100 centimetres cubed of 1.00 moles per decimetre cubed sulfuric acid and 15 grams of solid sodium carbonate by monitoring the volume of gas produced at room temperature and pressure, taking measurements every 15 seconds. To get the best possible answers, you're going to need to use the ideal gas equation, so that's good revision of Miss Forbes' work. I'm going to pause here. Don't forget, you can always go back and look at what I did on the previous ones. But here is the data that you need. I would like you to, please, by using your calculator, so don't just chuck it into Excel and try and work it out. Use your calculator, work out everything, make yourself a nice table for it. Then, if you have some graph paper, have a go at plotting it as a graph. I can't imagine most of you do have graph paper. You might be able to print some, or alternatively, once you have your final results, whack it into Excel and plot it as a graph for me. Okay, so I'm going to pause here. This will take you a while. Okay, hopefully you have managed to do all of that. When I did all of these calculations, this is what I got, and this is the graph that I got. Okay, so hopefully you have managed to get this far. Okay, if not, hopefully these results hopefully make some sense. Don't forget, of course, that you needed the equation, which I didn't tell you, but hopefully you know or can work it out. Come on, pen. H2SO4 plus C, no, plus, no, I don't want to change colour, plus Na2CO3 going to H2O plus CO2 plus Na2SO4. So it's a 1-to-1 ratio. So however many moles of carbon dioxide you have produced, you have used that many moles of hydrogen sulfide. Okay? Okay. There is another way that we can do this, which is to do, well, one of the things that we're most interested in is the initial rate of reaction rather than the rate of reaction over the entirety of it. And the rate of reaction, the initial rate of reaction, is just the rate at time equals 0. Okay? Hopefully you remember how to work out the rate at a particular time. Let's say if we wanted to do 200, you would, that's a terrible line. Let's get rid of that. You would draw a tangent You'll draw a tangent, my tangent's not touching, and it would be doing better for about 140, and then you would work out the gradient of that. You can do that using the big triangle. All the initial rates one wants you to do, if we have a graph that looks like this, is just do it at time equals 0. So all you do, I'm doing a terrible job of drawing tangents. I apologise. You do your tangent at time equals 0, and you'd measure the gradient of that. Okay. An alternative to that is to do a thing called a clock reaction. If you remember back to GCSE, we had an experiment where we had a conical flask on top of a cross, and you put sodium thiosulfate and hydrochloric acid in, and you timed how long it took for that cross to disappear. That is a clock reaction. What we're doing is we're setting it up so that we've got a visual change that we can see, and all we're needing to do is to take the time for that visual change to happen. So long as we've set this up properly, the initial rate is proportional to 1 over time. That's what this little symbol means here. Okay. Now there are a couple of things that you need to do. So you must make sure that, as it says at the bottom, the concentration of the reactants mustn't substantially change. You can get away with about a 15% change. Okay. That links into the visual change happening before there's a massive change in the rate. So long as your concentrations haven't changed a lot, your rate won't have changed a lot, and it's a pretty good estimation of what the initial rate was. If you let it go too long, it all stops working. Okay? But if you do it so that you've got enough of a time, then, or short enough time, then it will work. Okay? We're going to have a look at using these initial rates, either by doing clock reactions or by using the graphs and calculating what the initial rate is, to work out some additional information about our chemical reactions next time. So hopefully this has, a lot of it's been familiar. Next time we will be looking at things which